Hey, I've got another problem here today from the UNSW Integration Bee 2019. This one was problem 20. We have the integral from -3 to 3, x to the fourth over 1 plus e to the x dx. Okay, thought this one was really interesting. I like these kind of problems with the symmetry of the bounds. And that's what I'm going to do. We're going to just use that. And I'm going to make a substitution, adding these two bounds to get, adding the two values together. 3 minus 3 is 0. So we can look at it as 0 minus x, or just make our substitution u equal to minus x. And then of course from that we can see that x is going to be equal to minus u and dx is going to be minus du. So we'll make this substitution, and what that's going to do is just kind of change the sign on our bound. So plugging a 3 in, we have a minus 3, and plugging a minus 3, we have a 3. So it also kind of flipped it. Then let's see, so substituting in here for x, we're going to plug in a minus u to the fourth in the numerator. Then we're going to have just 1 plus e to the minus u, and then we'll have a minus du. And I'm going to take the sign out front and use to swap my bounds. So I'm just going to do a quick rewrite with the bounds flipped and this minus gone. You notice when you take an even power here, the minus sign is going to go away. So we're just going to have u to the fourth in the numerator, 1 plus e to the minus u du. One thing you notice when we've done like King's principle or any of these symmetry problems, we're usually trying to use our original integral and get it to look like that. And the big difference I'm seeing is this minus sign. So I want to kind of correct that. What I'm going to do, I'm going to multiply numerator and denominator by e to the u. So that's going to give us u to the fourth, e to the u in the numerator. And then when we multiply it in the denominator. Okay, the first term we're going to have an 1 times e to the u is e to the u, and then e to the u times e to the minus u is a 1. Noticing I changed the order because I want it to look like that. Not that I needed to, but just to make it clear. And then again, with an eye towards this first integral, I can change my variable. This is a definite integral. Okay, so changing the variable doesn't change the expression. So I'm just going to rewrite this whole thing in x and see where we are. Okay, now I like where we're at because you notice now we've got this comparing to our first, we're going to call our original integral I, okay, and we're going to say this is also I because all we've done is manipulate it. So this is equal to this. And notice we have the exact same denominator, we get the same variable, and we have the same bounds. So we're just going to take these two and add them together and see what we have. So I kind of skipped the step where it was two integrals, and I've combined this into one integral, and that's because we have the same bound, same variable. So now you notice like in the numerator we added x to the fourth to x to the fourth ex. But then from here what I can do is we could actually factor an x to the fourth out of this. Okay, and if we factor x to the fourth out, we have x to the fourth times 1 plus ex. But that's going to be exactly what we have here in the denominator. So we can actually cancel right there. And that's going to really simplify this thing, because then we just have an integral from minus 3 to 3 of x to the fourth. And then one really quick trick I'm going to do, that you don't have to do this step, but I kind of like doing it, is because this is an even function with symmetrical bounds, we can actually write this as going from 0 to 3 and just have it as two copies, because for an even function it's completely symmetric around the y-axis, so it allows us to do this trick. But doing that, we get this cancellation of this 2 with this 2. So then this value over here on the right is actually just going to be the value of our integral. So integrating x to the fourth is just power rule, and we get x to the fifth over 5 from 0 to 3. And of course we don't need to worry about 0 because that 0 is just going to be 0. So we just need to plug in 3, and we have 3 to the fifth, which is 243 over 5. So that's it. Thought it was a fun problem today. Thanks everyone for watching. Please like and subscribe. Have a great day.